All right, so in this video, we're going to talk about differentiation rules. And up until now, the derivative has been defined as the limit as h goes to 0 of f of x plus h minus f of x all over h. And you are probably sick and tired of running through those limits every single time you wanted a derivative. And you probably thought we were crazy telling you that you had to do this no matter what the function was. And while it works, it's certainly not the most efficient way most of the time. So understanding the fundamental idea of a derivative, where it comes from, what it does, is what we've been building up to till now. Now that we've got that foundation, we're ready to go ahead and say, all right, there are definitely better ways to find derivatives, especially when the functions get much, much messier. So in this section, we're going to talk about these properties. We'll start here with the derivative of a constant. And so when we talk about these properties, and you'll see this notation a lot throughout the course, I'm going to write d dx and then this of c. And so what this is saying is that the derivative of this function with respect to x. So x would be our independent variable. So the derivative of c with respect to x. And c is clearly going to be a constant in this case. And so the derivative of a constant, which may or may not surprise some people, is going to be equal to 0. Okay? Now, why? Why is the derivative equal to 0? Well, what is a derivative? A derivative represents change, represents slope. And if we think of this guy as our function, and we look at the graph of y equals c, well, the graph of y equals c is going to be a horizontal line. What is the slope of that horizontal line? Well, 0, right? And if we also think about, again, a derivative being all about change, well, does a constant change? No, by definition, it's constant. It doesn't change. So there would be no change in a constant. So the derivative of a constant is always equal to 0. Now, I always give this problem in class, or one similar to it, and the responses I get are pretty interesting from time to time, and there's no method to this madness. I'm just kind of writing stuff down. Okay, so maybe I'll call it an example here. So you've got pi raised to the 423 minus root 5 raised to the inverse sine of root 3 over 2. What is the derivative? If you said anything other than 0, you're working too hard. Remember, guys, these are all constants. Everything up here is a constant. I don't know what this is. This is just a number, though. It doesn't matter what the number is. If it's a constant, the derivative is always 0. No questions asked, because it's not changing. Okay, so that's the derivative of a constant. I'll go ahead and clear the screen. We will now look at the power rule. Okay, so power rule. The derivative of x raised to the nth power with respect to x is going to be n times x raised to the n minus 1. And yes, that is absolutely correct, as crazy as it sounds. Let me show you an example real quick. If we have, let's say, y equals negative 3x to the 12th. Well, y prime, first of all, before I get to y prime, let's cut to the chase here. If we didn't have this, I don't know anybody that would be willing to compute this derivative using that limit definition that we've studied up until this point. So you can see how these properties now are going to allow us to work with things that are much more complicated. But now back to this story. All I'm going to do is I'm going to take the n, I'm going to multiply it down, and in this case it'll be the 12 times the negative 3, which would give us a negative 36. The x stays there, and then I subtract the exponent by 1, which would be an 11 at this point. So the derivative of negative 3x to the 12th is negative 36x to the 11th. So all I did was essentially multiply down and subtract 1. So multiply that exponent down and subtract 1. Now, I remember as a calculus student, and I told you guys I took calculus over the summer as well, and even though we were moving at such a fast pace, I'll never forget the day I was told that this was true. I about fell out of my chair. This shouldn't be this easy, right? But it is. It really is. And so we're going to go ahead and prove this. Now, the proof of this The one that I prefer is going to be a proof using the binomial theorem. And so that was one of the problems that you worked in the pre-chapter handout. But just as a review, the binomial theorem allowed us to take a binomial a plus b to the n, which we know if we expanded that out by multiplying it, we would get a big sum. It would be the sum from r equals 0 to n of n choose r, a raised to the n minus r, it's an n there, times b to the r. And this n choose r is going to be a combination, n factorial over r factorial, n minus r factorial. I do have a video on my YouTube page in the algebra section where this whole concept is talked about. So if you need to go back and review it, if you haven't done so, please do so at this point. I'm going to box that in to get it out of the way, and we'll jump into the proof. So the proof is going to be us starting by letting f of x equal x to the n. And we're going to use our limit definition to show this works. So if this is the case, the derivative would be the limit as h goes to 0 of x plus h to the n minus x to the n all over h. So it's just our difference quotient with the limit out in front, standard limit definition of a derivative. So it's going to be this guy right here that we're going to be required to use this binomial theorem. And so once again, we're going to just write out the first two terms, knowing that the pattern would continue, and then we'll write out the last term as well, showing what happens there. So we have our limit as h goes to 0. Remember, carry that limit notation all the way down until you're finished evaluating. And it would start n choose 0. Okay, our power is n, and we start at 0. That's why we have this n choose 0. Our first part, our a value, if you want to call it that, would be an x raised to the n times our b value of h raised to the 0. Plus, because it's a sum, n choose 1, x raised to the n minus 1, h raised to the first. And so that would continue. You would have your next one would be n choose 2, x raised to the n minus 2, h to the second. So we're just filling the blanks in for the formula. Now, I'm going to skip the rest of those. And the last one, the very last term here, would be n choose n, x to the 0 times h to the n. So that's the very last term now, because we know that we stop at n. Excuse me. We know we stop at n. That's why we have the n choose n out in front. Our first x raised to then the 0, n minus n is 0, and then h raised to the n. Now we can't forget about this guy on the end as well. We still have to add the minus x to the n there. And that whole thing is over h. All right, so good news is that's the hard part. All right, so now I'm going to tell you a few things, some of which you might know, some of which you're going to want to pause the video and confirm on your own. But we know that h raised to the 0 is going to be 1. So this really doesn't come into play in this first term. X to the n certainly does. And this n choose 0, I would pause the video and I would go on a side piece of paper and I would run n choose 0 through your combination formula over here. When you do that, you're actually going to find out that n choose 0 is going to equal 1. So this guy here equals 1. We know that equals 1. The reason why that's so significant is because now all we really have up front is x to the n minus an x to the n on the back side. So those actually go away. And if you think about it, that's happened all along. I've always said if you've done this correctly, everything without an h should go away, and it did, which means that everything we have left, this guy, all of these guys, and this guy have an h in them. So we're going to take that h and we're going to factor it out. So if we factor the h out, it's going to now leave us with n choose 1, x to the n minus 1, and that h has been factored out. I'll go ahead and just write one more down because it's the easiest to see when you have the pattern going. Plus n choose 2, x to the n minus 2, now we would have an h to the first. Remember, I didn't even write it up here, but we know how the pattern works. If that's n choose 1, the next one's got to be n choose 2, and everything else follows. So this guy here would be an h to the first since I factored out one of the h's. Okay? And then that would continue all the way down till we got to n choose n, x to the 0, h to the n minus 1, because again, I factored the h out. All over h. Our h's finally go away. And if you're ready to evaluate the limit, you can see there's no h here, so that's not a problem. That's considered more or less a constant in this context. But there's an h there. It's going to go off to 0. Everything in here is going to have an h in it. It's going to go off to 0. That has an h in it. That whole thing's going to go off to 0. So when all is said and done, all we have left is this n choose 1, x to the n minus 1. And so that does look pretty similar to what we have up here, but we have some convincing to do. Is n choose 1 the same thing as n? Well, to figure that out, you're going to take the n choose 1, you'll run the same combination formula that you've been running, and after you do that, you would find out n choose 1 is actually n, and therefore the derivative of x to the n using the limit definition does turn out to be n times x raised to the n minus 1. So again, very, very interesting how such a complex idea has turned into such a simple technique at this point. Okay, so in this example, we're going to just find the derivative, and we don't really have many tools available to us other than the constant rule and the power rule, so we're going to have to manipulate this in such a way that we can use just those ideas. So before I get started, I am going to go ahead and simplify. Easiest way to move forward is to take this single term in the denominator, divide it up into each term in the numerator. In doing so, that's going to give us a 2x minus 3 plus 4x to the negative first minus 5x to the negative second. So now I'm at a point where I can now go term by term. When you take the derivative of a list of terms, you go term by term, and you'll multiply the exponent down and subtract 1. So for this first one, our exponent is 1. I'll multiply it down. I'll get a 2. And if I have a 1 up here and subtract 1, I get an x to the 0, which is just 1 itself. So that whole thing goes to just 2. Okay, now I'm going to stop for a second. I know that I've got a little bit more of the problem to do, but it's important to make note of this. I did exactly what the rule said. I multiplied down, I subtracted 1. But if we just focus on this and only focus on that, ignore everything else, this alone, ignoring everything else, would be a line. What's the slope of this line? 2. Hence the derivative being 2. Okay? So again, another way to double check yourself on some of these things. In the next term, derivative of a constant would be 0. So I'm just going to put a plus 0 in there. Finally, or not finally, but second to last, multiply the negative 1 down, you get a negative 4 times x raised to the negative second, and then a plus 10 x raised to the negative third. And for both of those, again, I multiplied down, subtracted 1, multiplied down, subtracted 1. And so this would be considered your unsimplified derivative. We'll talk a lot about unsimplified versus simplified derivatives in this course, but notice how I haven't really done anything to it. And in fact, I even have this additional 0 in here that doesn't seem to serve a purpose. But this would be your unsimplified derivative for this function.